Good morning, good afternoon, or good evening, whichever the case is. In this video, we're going to look at section 2.3 from the calc book, and now we're getting into some higher derivative rules. We'll look at a product rule and a quotient rule, and we'll talk about some higher order derivatives. So our bullet points for the section: find the derivative of a function with a product rule, find the derivative of a function with the quotient rule, find the derivative of a trigonometric function, and find a higher order derivative of a function. Okay, it says here in the last section, 2.2, you learned that the derivative of a sum of two functions is simply the sum of their derivatives. The rules for the derivatives of products and quotients of two functions are not so simple. So here's the product rule. The product of two differentiable functions, f is one function, g is another function. The product is itself differentiable. Moreover, the derivative of f times g is the first function times the derivative of the second function plus the second function times the derivative of the first. So here it is below in our beautiful calculus notation, d dx, the derivative of f of x times g of x. If they were added or subtracted, we would derive each function separately. But in this case, since they're a product, we have to do the first function f times the derivative of the second g prime plus the second function g of x times the derivative of the first f prime. Now, if I just write them both, our function names are f of x and g of x. If I just write them both here twice, f of x times g of x, it's like in each term, one function takes a turn being the derivative. Like in the first one, we can make f the derivative f prime times g of x plus, since f was already derivative in the first term, we're going to make g prime derivative in the second one. Now notice it's sort of backwards from what the book has written here. The product rule is very forgiving due to this plus in between. It does not matter what order we add two things in, as long as we're adding them together. So here f is the derivative, g is left alone. Here g is the derivative, f is left alone. And of course the big part of these will be the simplification that comes after the deriving. Now here's the proof. We're not going to even go through it step by step, but we want to find, the derivative of these two things multiplied. So here's back to our difference quotient, f of x plus delta x times g of x plus delta x minus f of x times g of x. And what they do here in red, they add and subtract the exact same quantity. It's like adding 2 and subtracting 2. You're not going to change anything. But what they do is regroup, and here they factor out the f of x plus delta x. Here they factor out the g of x, and then they do a little manipulation to get it look back to its the definition of a derivative, and we come up with this new product rule. And what's this? Whoa, I guess I just cut that corner there. The product rule can be extended to cover products involving more than two functions. Like let's say we have three functions, f and g and h. Well, that derivative here, if I underline this one in red, the first function, f, is the one that got derived to be f prime. And then we've got plus the next term is the same f and g and h, but in this case the middle term g is now derived to g prime. And we have another term, another plus f of x, g of x, h of x, but now it's the h of x's turn to be derived to h prime. So here's an example. If we had like a x squared, the derivative of that would be 2x, and then we've got sine and cos. So it's the derivative of the first thing, 2x, we leave the other two alone. Here we left the x squared and this cos alone, but we derived sine to cos. And in the last one, x squared we left alone, sine we left alone, and the last term, cos, was derived to negative sine. So this can be extended to any number of products. And here we go. Find the derivative of this. Now the way I've come to do these, I think I did this way when I was in high school, and I've been showing my students, of course. Here's our first term. What is the derivative of what I underlined in red? Well, derivative of 3x is a 3, and then we're going to have a minus 2 times 2 is 4, 4x to the first power. So that's our first function and its derivative. Here is our second function. And I'm going to put its derivative down here in blue. The 5 derives away, 4x derives to 4. So now when I started writing it like this, you know, the function's on top, the derivative right below. To apply the product rule, I'm going to do the first function times the derivative of the second. That's going to be like cross multiplying, plus the second function times the derivative of the first. And because the plus is in the middle, you can sort of do it, you know, backwards and still get the right answer. But this is just it, from the way it's set up, kind of like cross multiplying. So I'm going to cross multiply on this diagonal first. I'm going to put the 4 first, and then I'll have my 3x minus 2x squared. And then plus, we multiply on the other diagonal. 5 plus 4x times 3 minus 4x. Okay, let's do some algebra. Distribute the 4. 12x minus 8x squared. And then plus, here we're going to FOIL. First times first will be a 15. Our outers will be a minus 20. Inners a plus 12. So that's minus 8x. And then we multiply last times last, minus 16x squared. And let's put this in nice descending order. The negative 16 and negative 8x squared will combine to a negative 24x squared. Minus 8 plus 12x, that's a plus 4x. And we have a plus 15. And there's our derivative with the product rule. Because these two functions were multiplied, we can't just take the derivatives and multiply them. We have to do this first times the derivative of the second plus the second times the derivative of the first. Now this, it's a good one to show you the mechanics of a product rule. If I had to do one of these, say on the AP test, I would first FOIL and then derive with the power rule. So we can do that to check our work. Let's derive or FOIL out here. You know, 3x times 5, that's 15x. Outers would be a plus 12x squared. The inners would be a minus 10x squared. And then last times last, minus 8x cubed. And let me write this in descending order. Negative 8x cubed goes first. Here we're going to have a, what's that, a plus 2x squared. And then a plus 15x. So this is still our function h of x we have not derived. Here, down here at the bottom, that is our h prime that we got with the power rule, or the product rule. Let's say if we derive this, if we get to the same answer. Here, our power rule we would multiply and get a negative 24. X to 1 power lower, that term looks good. 2 times 2, that'll be a 4x to 1 power lower, 4x to the first. Plus 15x to the first. That x to the first derives away, so it's just 15. There is our h prime. It looks the same, so we did everything right. So the way we did it first, we did calculus first and simplified by algebra. The other way was we did the algebra first, and then the calculus did not need simplification afterwards. If you want to review simplifying expressions, you can always go to the algebra review back in the back of the book in the A appendix. All right, now here's one we're going to have to use the product rule on. We've got an x and it's multiplied by e to the x. It seems every year some students have trouble identifying that there are in fact two functions. Look for two variables. Here we've got an x, that's its own independent function. And then we've got an e to the x, another variable. So this is two functions multiplied together. And let's do it like this. The derivative of x to the first is just 1. The derivative of e to the x is e to the x. It is its own derivative. So let's derive. We are going to derive y with respect to x equals. Our first function is x times the derivative of the second, e to the x, so we sort of multiplied on this diagonal, plus we're going to multiply on the other, 1 times e to the x, 1 e to the x. Now we could leave our answer like that, Or we can see that there is a common e to the x to each term. Let's factor the e to the x out, and that'll leave an x plus 1. X plus 1. And it's derived and simplified as far as we can go. Ooh, this one looks fun. Find the derivative of, let's take a minute here and look at this function. 2x times the cos of x minus 2 sine x. Now that first term is going to be a product rule. I'm going to sort of rewrite it down here. Y equals, our first function is a 2x, and we're multiplying that by a cos of x. That's a terrible s. That's a little better. Cos of x. And then we've got this other term, minus 2 sine x. Notice here there's only one variable. There's just an x with the sign, sine x. So this is just a constant multiple times sine x. Okay. Dy dx, our derivative. Let's see here. The derivative of 2x is going to be 2. And the derivative of cos is minus, that's supposed to be an s, minus sine x. So first we got to apply our product rule. We're going to multiply on the diagonal. 2x times minus sine x will be a minus 2x sine x. Plus, we multiply on the other diagonal, 2 cos x, 2 cos x. And now we've got to derive this sine to cos. And the 2 is just a constant multiple, so the derivative will just be a minus 2 cos x. Ooh, and it looks like we'll have a nice simplification. We've got a plus 2 cos x, a minus 2 cos x. Those are going to combine to 0. And our final answer then is just the minus 2x sine x. What's this hiding in the corner? In this example, notice that we can use the product rule when both factors of the products are variable. You can use the constant multiple rule when one of the factors is constant. You know, this 2 sine x, we did not do the product rule on it. If you accidentally do, it might still work out because the derivative of 2 would be 0 and the derivative of sine would be cos x. So when you do the product rule here, you'd have a 0 times sine, which is going to cancel out. All right, we've done products. Now quotients. What if we have a function like this? What if we have sine x up top and e to the x downstairs? Do we just derive sine into cos and e to the x is its own derivative? No, that's too simple. It's not going to work. We have to use the quotient rule when our function is in the form of a quotient. And here it is, the quotient f over g of two differentiable functions, f and g, is itself a differentiable function at all values of x for which the denominator is non-zero. Moreover, the derivative of f divided by g is given by the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, all divided by the square of the denominator, as we see right here in the notation. Is that crystal clear? Okay, moving on. I'm sorry about that. Let's back up. It looks very confusing, and when you read through that, it is quite a mouthful. But what we have are two functions, f and g, and if we look at just the numerator, it's very similar to the product rule. The very dangerous thing is here, this is a minus. So you have to get the numerator in the proper order. If we flip-flop the terms, you're going to get the wrong answer every time. So it starts with g of x times the derivative of f minus f of x times the derivative of g. And look at our denominator. The quotient rule has this denominator, and it is our g of x function. Notice it's not derived, just g of x quantity squared. Now, if you're wondering how in the heck are you going to remember it, here is a little trick. For a quotient, we've got a high function and a low function. The high function is on top, the low function is on the bottom. If we derive the high function, you're going to get d high, the derivative of high. If you derive the low function, you get d low, the derivative of the low function. So we can now turn the quotient rule into a little song. Low d high minus high d low, square the denominator, off we go. Low d high minus high d low, square the denominator, and off we go. And again, you got to start it the same way. It is low d high. Low is our g function. Low is g, d high is f prime in this case from the theorem. So you have to start it off low d high. There's a little, the proof to this does employ the same tactic. We add and subtract the same quantity here in the middle, rearrange the numerator so we can factor stuff out and get back to our limit definitions. Here we go. Find the derivative of f of y equals 5x minus 2 up top. X squared minus 1 is the denominator. Here is our function. And again, we're going to kind of do a little pattern, a little crisscross thing here. So if I get my function right there, my high function is 5x minus 2. The derivative of that would just be 5. My low function is x squared plus 1. Its derivative would be 2x. So our function is y. Let's use y prime for our derivative notation. And here is going to be our numerator. We start with low d high. So low is x squared plus 1. Multiply that by d high, 5. So we're kind of multiplying on this diagonal, like we're cross multiplying. Low d high minus high, 5x minus 2, d low. I'm going to put that in front. So there it is, low d high minus high d low. Square the denominator. And off we go. So in there we're going to have x squared plus 1, quantity squared. All right, the calculus is actually over for this example. From here on out, it's just algebraic simplification. So here's my divider line. Let's distribute the 5. 5x squared plus 5. Here we're distributing a negative 2x, so that will be a minus 10x squared plus 4x. Now this denominator, we're not going to FOIL that out, because if we FOIL it out, it's going to get bigger and possibly messier. Leaving it like this quantity squared is much more concise, and there's always the opportunity that something might cancel. We might get a term in the numerator that would cancel one of those out. Y prime equals. And it looks like we can simplify a little more in that numerator. So we've got some x squared terms. Y prime equals. We got a 5x squared and minus 10 more, so that's minus 5x squareds. We've got a plus 4x and a plus 5. And then that's all over top of our denominator here, squared. And we see a little technology box down here. A graphing utility can be used to compute the graph of the function with the graph of its derivative. For instance, in the figure below, the graph of the function from example 4 appears to have 2 points that have horizontal tangent lines. What are the values of y prime at those 2 points? So it looks like here's our function, the original one in red, and then we have the derivative function in blue. All right, here, rewriting before deriving. Find the equation of the tangent line to the graph of, here's our f of x, 3 minus 1 over x is our numerator, x plus 5 is our denominator, and they gave us a point. Because they did say find the equation of a tangent line. So at the end, we're going to have an equation like y equals mx plus b that will be tangent to the graph at that point. Now the strategy here, it does say rewrite before deriving. Let me rewrite my function here. Y equals 3 minus 1 over x, all over x plus 5. Sometimes people aren't big fans of denominators, and they might want to multiply through and clear out any denominators. And here our denominator in the numerator it appears a variable x, but that's not going to hurt anything. Let's distribute an x in the numerator and also one in the denominator to see what happens. So we'll have a 3x minus, that would be 1x over x, or just 1. Our denominator, we distribute the x and get an x squared plus 5x. So here's our function rewritten before we're going to derive. All right, let me switch to black ink. Our numerator will derive to a 3x minus 1 just derives to a 3. Down in the denominator, it's going to be a couple terms. X squared derives to 2x plus 5x derives to 5. And let me get a little more room here. So notation, the derivative of y with respect to x. And remember, this always starts low d high. So low is x squared plus 5x times d high would be 3. Low d high minus high 3. That's supposed to be a 3. 3x minus 1 times quantity 2x plus 5. And that's all over denominator squared. X squared plus 5x quantity squared. If you are thinking about canceling like this, can't do it because on the other side of minus there's another term and that is not present in the other term. Okay, the calculus is over. Now it's just some good old algebra. The first piece of the numerator is not bad. I might have to drop my notation just so I have enough room. We're going to distribute that 3. 3x squared plus 15x. Now be careful. This is a minus, and we're going to FOIL this out, obviously, but we're still subtracting it as a quantity. You know, we're minusing those two things multiplied, so we have to FOIL them out, distribute the negative before we do any more combining. So let's start FOILing here. First times first, 6x squared. The outers will be a 15x, the inners a minus 2, so that'll be a plus 13x. And then last times last is minus 5. And that's all over x squared plus 5x quantity squared. Now we distribute the negative and combine like terms. And I'm going to do that all in one step here. So let's put our denominator downstairs where it belongs. X squared plus 5x quantity squared. So let's see, when we start distributing the negative, this first term will be a minus 6x squared. We've already got a 3x squared, so that leaves us with a minus 3x squared. We'll distribute the negative here. That will be a minus 13x. 15x minus 13x will be a plus 2x. And we distribute the negative to the 5, where it becomes a plus 5. So there is our derivative. Was I using y prime or dy dx? Whatever, there we go. So we've got our derivative. Now remember, back at the start of the problem, they wanted the equation of a tangent line at a specific point, negative 1, comma 1. We need two things to write the equation of a tangent line: a point, which we have. We need a slope occurring at that same point. And we use derivatives to find slope. So let me go back. We'll call this f prime of, we're going to plug a negative 1 in there. A negative 1 goes in for x. So this will turn into a negative 1. We'll square negative 1 to get 1, and then that gets multiplied by negative 3. This plus 2 times x, this will be 2 times negative 1. That'll turn into a minus 2. And then plus 5. And then, our numerator turns into a 0. Let's see what happens downstairs. This x squared will be a negative 1 squared. That'll turn into a 1. And then 5 times negative 1 will be a minus 5. So that's negative 4 when we subtract and we square it. Negative 4 squared is 16. 0 divided by anything is 0. So it looks like our slope is 0. M is 0. And our point is negative 1, 1. Y minus y sub 1 equals m times quantity x minus x sub 1. That'll turn to a plus, and we'll distribute the 0. That'll wipe out both terms. And if we add 1 to both sides, y equals 1. Looks like our tangent line. Let's see, down in the corner I see graphical solution. Let's see what that looks like. So here's our original function. Use the tangent line feature to determine the equation. And when we see that right there at the point of tangency, that blue line is nice horizontal. That's our line y equals 1. We're tangent to the graph of that function at the specific point that they asked for. Okay, what's next? Here, using the constant multiple rule. The book says not every quotient needs to be differentiated by the quotient rule. For instance, each quotient in the next example can be considered a product of a constant times a function of x. In such cases, it's easier just to use the constant multiple rule. There's less steps involved. Like this first one here, x squared plus 3x over 6. Sure, it is in the form of a quotient. We could take the derivative of the high, 2x plus 3. Derivative of the low would be 0, and it would work. But here, we can, mentally think about dragging that denominator 6 out. And if you drag it out as a denominator 6, there's still a 1 up above it. That's 1/6. And then what we have left will be our function, x squared plus 3x. So now we can derive the derivative of x squared plus 3x will be a 2x plus 3, and we can just multiply that by the 1/6. So what we can do is just now at the end, put that 6 back in the denominator. So the 6 goes back underneath, and we got a 2x plus 3 upstairs. So drag the denominator out, but make sure you keep it a denominator. This one here is pretty similar, but the numerator is just a single term. And notice there's just that x to the 4th. It looks like it's attached to the 5. We can let, that x to the 4th sort of fall off. As long as it doesn't wind up distinctly in the denominator, we're fine. Now we can derive with the power rule. We multiply our exponent by what's already down there. 4 times 5 over 8 will be 20 over 8. And then we'll have our variable x, but now it's down 1 power to the 3rd power. And we can reduce that fraction there. It looks like we can divide by 4 and get 5/2 x to the 3rd. And if you want to put the x to the 3rd back up in the numerator with the 5, that's perfectly fine. As long as you don't put it distinctly down in the denominator with the 2, to do that you'd have to change the exponent to negative. Letter C. Ooh, look at this one. We've got a few things going on here. A negative 3/7 out front. We've got an x downstairs. Now what we can do here, again, we could do the product or the quotient rule on this, but it would turn into quite a mess. Notice in the numerator, it looks like they forgot to factor out an x. So I'm going to sort of come down here below. We've got this minus 3. And inside the parenthesis, there's an x and an x squared. So let's factor that x out with the negative 3. And that will leave us a 3 minus 2x. The denominator underneath is 7x. Aha! Since we factored that x out, we can now cancel. So now what we've got, I'm going to come back up here. I can put this in the rewrite section. We've got a fraction out front, negative 3/7, and that's going to get multiplied by 3 minus 2x. So again, the negative 3/7 is a constant. We can derive this function that I just underlined in red and then multiply it by that same constant. So the constant does come along, negative 3/7 times. When we derive in the parenthesis, the 3 derives away, negative 2x derives to negative 2. And then we can just multiply those together. Negative times negative is positive. 3 over 7 times 2 over 1 will be 6 over 7, 6/7. Letter D. Now this one, we've got, it's kind of similar to the or a different one, but now the x squared is distinctly in the denominator. Now for the rewrite, we can move that denominator out of there. We're just going to move it up where it's going to change sign to a negative exponent. Now be careful, the 5 has an exponent 1. The 5 is not going anywhere, it's staying down there. The x squared escapes the denominator where it becomes x to the negative 2. Now I don't know, have we done one with a negative exponent yet with the power rule? You know, the power rule still works with negative exponents. So we're going to multiply this exponent times 9/5. That will be a negative 18 over 5. And then we're going to have x, and we're going to drop it 1 power, down lower to negative 3. And we don't leave negative exponents in our final answer. It's just bad manners. So our fraction is negative 18/5. Now we're going to move that x to the negative 3 back to be distinctly in the denominator, where it changes to x to the 3rd. Okay. What's this down here? To see the benefit of the constant multiple rule for some quotients, try using the quotient rule to differentiate some of those. And we're not going to do that. It's a lot more work, but you should get the same results. Remember, the AP examination is timed. It's important to be efficient. Recognizing ways to rewrite a problem before you solve it, like we just saw in this example, can accelerate you through the and your progression through the exam. All right, here, I don't do many proofs in this class, but this is a good one. The power rule for negative integer exponents. So here we want to derive the notation there, d dx. We're going to derive with respect to x, x to the nth power. And what we want to do, it's d dx of 1 over x to the k. Let me do it like this. Well, because they give us this setup here. N is a negative integer. So n is negative. They want that n up there to be a negative integer. Then there exists some positive integer k. We could just rewrite that n as a negative k. So by the quotient rule, we could write this. Derivative of x to the n, d dx, 1 over x to the k power. So all we did was just sort of rewrote this. This was x to some negative exponent, and we rewrote it as x to the k power, where that n, we just replaced it with a negative k. Now watch how slick this is. I'm going to just rewrite this a little bigger. 1 over x to the k. Now if we do the quotient rule on this, the derivative of the high function, 1 is just a constant, derives to nothing. Down here, if we derive x to the k power, that would be, we bring the exponent down front, so that would now be k times x to 1 power lower. We'll take the old exponent k and subtract 1. All right, let's do the quotient rule. Here's my divider line. We start out low, d high. So here's my low function. It's going to get multiplied by 0, which is my d high. 0 times x to the k. That's supposed to be a k. Oop, that's just terrible. X to the k. There's low d high minus high d low. Our high function is 1. We're going to multiply that by the k, x to the k minus 1 power. Low d high minus high d low. We're going to square our denominator. That's going to be x to the k times itself times x to the k. And what do we do with the exponents if we multiply like bases? We add them. So that's going to be x to the k plus k power, or 2k. All right, a little more simplification is coming. So that 0, there it is, 0 times this will be 0, so that just gets zeroed out. Negative 1 times this is just going to be negative kx to the k minus 1 power, and this is over x to the 2k. Now there is a minus k in that numerator, but that's just a number. And look what's going on here. We've got the same bases. We're dividing the same bases. So what do we do with the exponents? We subtract the exponents. So our answer here, we're going to have the minus k, that number. And we know we're going to have base x, and the exponent up here, let me switch to red ink, we'll take the numerator exponent, k minus 1, and we're going to subtract the denominator exponent, 2k. K minus 2k, that'll turn into a negative k minus 1. Negative k minus 1. Now to get back to where we started, we're going to replace negative k with an n. Remember, that was our substitution here at the beginning. Take out a negative k, replace it with an n. So this negative k and this negative k will get turned into n's. So that'll be n x to the n minus 1 power. So we just proved that the power rule will work on negative integer exponents. Fun stuff. The trig functions. Definitions of the trigs. We know that the derivative of sine is cos, and the derivative of cos is sine. Here are the other derivatives. Now, before I read through them, let's see how our founding fathers in calculus figured these out. So at some point in their mathematical careers, they figured out the quotient rule, and they were trying to figure out the derivative of tangent. And they did not have a good starting point besides turning tangent into sine divided by cos. So sine over cos, let me put my x's on there. Let's think quotient rule. Derivative of the high. What's the derivative of sine? Cos x. D low. What's the derivative of cos? Negative sine x. So the quotient rule says, let me give myself a little room up here. Low D high. Cos x is our low. D high is also cos x. So low D high is cos times cos, which is cos squared x. Low D high minus high D low. So our high function is sine. D low is negative sine. Sine times sine is sine squared. So that will be negative sine squared x. Low D high minus high D low, square the denominator, off we go. So our denominator was cos x, that will be squared. In the numerator, minus a negative turns to add the opposite, that turns into a plus. Sine squared plus cos squared. I hope you remember enough pre-calc to remember that sine squared plus cos squared is equal to 1, so that becomes 1 over cos squared. And the reciprocal identities, 1 over cos squared is secant squared x. And that's up here in our derivative theorem box. The derivative of tangent is secant squared. So these are not as simple as the derivative of sine is cos and the derivative of cos is negative sine. Let's take a nice look at these derivatives of the other trig functions. Of course, these are going to need memorized. The derivative of tan x is secant squared x. The derivative of secant x is secant x times tan x. The derivative of cotan x is negative cosecant squared of x. The derivative of cosecant x is negative cosecant x times cotangent x. Do you have those memorized? Good. Let's dive in. Oh, let's back up. I do have a little trick to memorize these. I found it in a book called Calculus for Dummies. I've sent many students off to college campuses colleges with their calculus knowledge, and they have shown this to calculus professors at their colleges who had never seen this before. So you don't just have to memorize these, you just need this little mnemonic. Like let's say you're taking a test and these come up and you don't remember the derivative of tangent, so you're trying to cheat, you're trying to get a hold of the person sitting closest to you, and you're trying to discreetly get their attention by saying psst, psst. You're just trying to make a little noise to get their attention. Psst. Well, let's drop off the letter P. SST. SST. Secant, secant, tangent. Right below, we give them a co. Secant gets a co, that becomes cosecant. This secant gets a co, that also becomes a cosecant. This tan gets a co, which makes it cotan. So we do our secant, secant, tan, right below each, give them a co, and we have to remember to negate this middle cosecant. Now we've got a table. We can read it left to right or right to left. Let's start here. I'll switch to green ink. The derivative of secant are these two multiplied. So the derivative of secant is secant times tan. Derivative of secant x is secant x times tan x. So there it is above. Back up here. The derivative of cosecant are these two multiplied together. So the derivative of cosecant, negative cosecant, cotangent. Here's derivative cosecant, negative cosecant x times cotan x. So there we read the table left to right. Now we can go right to left. The derivative of tangent are these two multiplied. The derivative of tangent, secant times secant, is secant squared. And right below that, the derivative of cotangent are these two multiplied. Derivative of cotan is negative cosecant times itself is negative cosecant squared x. So there are the derivatives of all 6 trig functions. Let's try it out. The first one, function y equals x minus tan x. So we just derive this in pieces. dy dx, the derivative of y with respect to x. Derivative of x is just a 1. And then we have minus. The derivative of tangent is secant squared x. Letter B. Ooh, look at this. It's multiplied. Looks like we're going to have to do a product rule. Our first function is x, and the derivative of x is just 1, so that's not too bad. The derivative of secant x is secant x tan x. So it's time for the product rule. Let's use y prime for our derivative notation. The first x times the derivative of the second, secant x times tan x. So there's first derivative of the second plus the second secant x times the derivative of the first 1. So I'm not even going to write it in there. Now it looks like we could simplify, I guess. We could factor a secant x out. Here on the left we have a secant x in the first term, and we have a secant x here, so let's factor that out. Our derivative equals secant x times, since we factored that out, there's going to be an x times a tan x, x times tan x, plus we factored that secant out entirely, so there's a plus 1 left there. And there's our final answer. Now here, different forms of a derivative. If you remember back in pre-calc when we were proving identities, you might have seen something like this in pre-calc that said make the left side match the right side. So the left side we'd bust it up, 1 over sine, that's the same as cosecant. Cos over the sine is the same as cotan. So these are equivalent expressions. And what we're going to do is derive them each and look how different our derivatives can turn out. Let's see, so if I look at this one, I'm going to derive it with the quotient rule. Here's our function up top, the derivative of high. 1 is going to derive away. We've got a minus cos. Cos is going to derive to negative sign, which will hit that negative and turn it into positive. So our d high is just sine. And then our d low, the derivative of sine, is cos. So if we start doing the quotient rule on this side, and I'm probably going to need to move this. We've got low d high. Low is sine times d high is also sine. So that will be sine times sine. dy dx equals low d high. Sine times sine is sine squared. Low d high minus. Now we're going to do high d low. Our high function is the 1 minus cos x quantity. And our d low is cos x. Cos x. Low d high minus high d low. We're going to square the denominator. Sine x times sine x is sine squared. Okay, we can do a little simplifying here. See, if we distribute this negative cos, that'll turn into a minus cos of x, but then this will turn into a plus cos squared. So up there, we already had a sine squared of x. We'll distribute and get a minus cos x and a plus cos squared x. All over sine squared x. Now, even though they're not right next to each other, we do have a sine squared plus a cos squared. And we saw, I think, just in the last example, that sine squared plus cos squared, well, that's just going to turn into a 1. So we're going to have a 1 to keep the minus cos x company. 1 minus cos x. And that's over sine squared. So remember where we started, I sort of drew this divider line. We derived this to get down here to its derivative, y prime equals that. Now what do we got over here? Well, we can derive this separately. The derivative of cosecant from our new rules is negative cosecant x times cotan x. And then we've got a minus cotan squared will turn into a negative cosecant squared. The negative negative will make that positive. So we'll have a plus, and I just squeeze it down here, cosecant squared x. Are those the same? And let me rewrite it down here. I'm going to put this term first, cosecant squared of x, and then we'll have our minus cosecant x cotan x. Now we could factor out a cosecant, but let's play with what we have over here on the left and see if we can get it to match right now. So this one, if we break it into its two separate fractions, notice the denominator is a single term sine squared. We'll have our numerator 1 over its own sine squared minus cos over its own sine squared. Okay, we're really close. You know, this 1 over sine squared would flip. Its reciprocal is that cosecant squared. And we can rewrite this one. We could pull out, pull this denominator apart, so it'd be cos over sine times sine. Cos over one of those sines is going to turn into cotan, and we'll have a 1 over sine, which turns into cosecant. So even though they look very different, they're still going to be the same derivative. You know, we could graph the original functions in the y editor of a TI-89. The original functions would look identical. When we solved and got the two different looking derivatives, we could graph those. Those graphs would look exactly the same. You know, just because they look a little different, you know, it's the same function. The graphs will be the same. Because of trig identities, the derivative of, can take many forms, blah, blah, blah. I already said that. All right, the summary below shows that much of the work in obtaining a simplified form of a derivative occurs after the deriving, after the calculus is over. You might have heard me say last year in pre-calc that calculus is not hard. It's the algebra that might bog you down. And then the book says, note the two characteristics of a simplified form are the absence of negative exponents, no negative exponents, and you do want to combine your like terms. So here in example 1, right after the calculus was over, this was our raw derivative. After we simplified it, looked a lot nicer. Example 3, product rule gave us a pretty nasty raw derivative. Simplification made it a lot nicer. Example 4, quotient rule. Raw derivative was pretty nasty. Simplified down was much nicer. Example 5, same thing. Quotient rule, raw derivative, simplified. Example 9, quotient rule gave us that raw derivative. Simplified was much more concise. All right, higher order derivatives. You just keep deriving. If you have, say, x to the 10th, the first derivative would be 10x to the 9th. Derive it again. 90x to 1 power lower. That would be here's our original function f. There's your first derivative, second derivative. Your third derivative would be, 720x to the 7th. And you can just keep going. Eventually, you might wind up at 0, but we can do lots of derivatives. So just as we can obtain velocity by deriving position, we can obtain acceleration by deriving velocity. Another way to look at this is that you can attain acceleration by deriving the position function twice. So here, just pay attention to the notation. These real-world applied problems have their own special notation. S of t, t for time, is our position. If we derive position once, we get s prime, or just simply velocity. If we derive velocity once, we get acceleration. Or if we derive position once, we get velocity. Derive position twice, we get acceleration. Now what we're going to do here is just compare and contrast some of the notational differences. The first is just simple prime notation. Y prime is your first derivative. Y double prime would be your second derivative. Y triple prime, third derivative. Now watch, after third derivative, you'll see something. It would typically be an exponent, but they put it in its own little set of parentheses, so you know it's not an exponent. That will denote a fourth derivative. Anything higher than that, you'll just have a number inside those parentheses. For the function notation, we could do f prime of x for first derivative, f double prime of x for second, f triple prime, and then the fourth derivative of x. So very similar to prime notation with the function thrown in there. Now my personal favorite is the Leibniz notation. And remember, Leibniz would be dy dx, the derivative of y with respect to x. Well, no, that would be the first derivative. Our original function is y, so the first derivative would be dy dx. Now, if we're going to derive it again, the second derivative of y, d, it looks like squared, d squared y over dx squared, the second derivative. And now those are sort of like exponents. Those will just go up. The third derivative, d3y over dx3. And then it would just continue on like that for any numbers beyond. And, that's where we'll stop. Those are the most common. You'll see the y prime, the function prime notation, and good old Leibniz. And what do we got down here? I think I already covered this. Yeah, y double prime, y triple prime, blah, blah, blah. All right, acceleration due to gravity. So it says, because the moon has no atmosphere, a falling object encounters no air resistance. Back in 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these falling objects is right here. So they have this position function. This is just for the moon. S of t is height in meters. This one's in meters. T is in time in seconds. Now we might do like a little side by side. Earth, moon. Let's see here. The moon, we have its position function, S of t, negative 0.81 t squared plus 2. The position function in the last section, when we did right before the diver off the diving board, we had the generic Earth's position function, and that was 1/2, and then there was a g in there. That was Earth's gravitational constant. On Earth, that was a negative 9.8 meters squared, and that would be 9.8 times t squared. And then we had our other stuff plus v sub o times t plus v sub o. Or, excuse me, s sub o, initial height, s sub o. So we're going to derive each of these twice. Now, I wrote the Earth one here. It sort of bled over here into the moon part. So let's derive this once and then derive again. S prime t. Now, I could have multiplied the half by the negative 9.8 and then derived. But if we do the power rule here, that 2 is going to hit that 1/2 and turn into a 1 times the negative 9.8, and then we'll have t to the first power. So there is our first derivative on Earth. Ooh, that eraser was a little too big. There we go. So that is Earth's velocity function, s prime of t. Remember, we could have used v of t. S prime and velocity are the same thing. Now, if we derive again acceleration with respect to time, if we derive negative 9.8 t with respect to t, we just get the negative 9.8. If we do the same thing over here on the moon, derive position to get velocity, that's going to be negative 2 times 0.81 is 1.62. T to the first, and the 2 derives away. If we derive that velocity, we get the acceleration constant on the moon. The t to the first derives away, and that's just negative 1.62. Now I'm going to go back, read the last line of the setup to the problem. What is the ratio of Earth's force to the moon? So we can do Earth first and then moon, or we could do it as a fraction. Let's do it as a fraction. Earth will be the numerator, moon in the denominator. So Earth, we had our negative 9.8, our moon in the denominator, negative 1.62. If we divide those, the negatives will cancel to be a positive, and we get, we'll round this off, approximately 6.0. So the moon's the Earth's gravitational force is 6 times that of the moon, or the moon would be 1/6 the gravity of Earth. And I see something down here. Here's a different way you could get to this using mass. The moon's mass, 7.349 times 10 to the 22nd power. Here's a good real-world application of scientific notation. That many kilograms. Earth's mass is 5.976 10 to the 24th, higher exponent, kilograms. The moon's radius is 1,737 kilometers. Earth's radius, 6,378 kilometers. Because the gravitational force on the surface of a planet is directly proportional to its mass and inversely proportional to the square of the radius, the ratio of the gravitational force of Earth compared to the gravitational force of the moon, when you do that dividing out, you still get the same 6.0. That is the end of this video. Here is the assignment, the even problems from the textbook. There are 6 questions on the WebAssign. Have fun.